All right, so today I'm Gersi Doko, and I'm going to be talking about Varuna, which is a scalable, low-cost training of deep learning models. And the basic idea in this paper is that they want to make the training of deep learning models as cheap as possible and use as many resources that are unutilized or underutilized as possible. So these deep learning models are becoming more and more apparent in different research areas. So we have language models, mathematical simulations like fluid dynamic simulations. We have RL, which uses large MDP value spaces that are approximated by these deep learning models. And we have query response optimization. These are just to name a few of the areas where ML is being increasingly used, and not just increasingly used, but used at a scale that has not been seen before due to the restrictions of the compute available. Just to name a recent development that was just released at the beginning of June, GPT-3, which is OpenAI's new language model, has approximately 175 billion parameters. So that's the extra large model size. And it has achieved state-of-the-art performance in different language tasks. So these models are going to continue to scale in their parameter size, and the cloud has to be there to support these models in a way that's cheap, effective, efficient, and all that good stuff that the cloud does. So the current training methods and the current software that's out there to train these models, they require uniform GPU configuration, which is usually achieved via the use of hyperclusters. These hyperclusters are almost exactly what they sound like. They are just huge, huge machines that have a lot of memory, a lot of compute. These GPUs are beefy, and they have huge bandwidth connections. We're talking about 200 gigabits per second. And these machines, these are widely used because they thought, hey, the bigger the machine that we use, the faster we can do it. But that's largely not the case anymore. They would now prefer to use smaller machines that are cheaper and actually get faster performance because they're scaling it so much more. So we want to be able to scale with more machines in a more efficient way. So that's the purpose of this paper. So instead of using hyperclusters, where the data can't fit on one machine anyway, then why can't we just use low-cost, low-priority VMs and deal with the implications that those bring? So the solution that this paper brings is let's be as thrifty as we can with everything that comes with using cheaper VMs. So low-priority VMs are 5 times cheaper than hyperclusters, than dedicated hyperclusters. And these hyperclusters, normally, they are dedicated. So these machines that are now being preempted in slow network configurations, the VMs I'm talking about here, we would like to abstract away their uniformity. So we don't want to necessarily assume that anymore that we're using the same GPUs across different machines. Now we actually just care that, hey, let's make huge clusters of these VMs, and if some of them go down, we'll try and manage that and we'll overcome the complications. And that's just be happy that we're saving cost and improving model training efficiency. And they are going to achieve that in a number of ways. So, I'm sorry. They're going to achieve that in a number of ways. So they're going to partition the data to run across multiple replicas, and they're going to maintain the snapshots of each training phase so that you don't lose anything for VMs going down, or the whole pipeline phase has to be restarted from the checkpoint. And the problems that I've just outlined that come with this thrifty approach are the slow and flaky network that usually comes along with those VMs. You no longer have these 200 gigabit per second bandwidths. So you can't transfer all of this data that you're used to on the hypercluster. So you have to be a little bit smarter about what data you transfer when and how it affects the pipeline efficiency and the machine efficiency to keep machines from becoming too slow and slowing down the rest of the pipeline. We have to deal with the transient resources of each machine. Each machine is preemptible now, so it's not a dedicated hypercluster anymore. This is a group of low-cost VMs, so these resources are transient. So you have to deal with that. And of course, you have to deal with the transparency to the user. So the user is currently used to writing code that runs on this GPU, and they cloud provider comes and says, okay, we have this hypercluster of this GPU. You write your code for this GPU and it runs just fine. So with Varuna, we have to have a model where we have to have a program where it doesn't matter if different machines are using different GPUs. We have to be able to accommodate different VMs. And the solutions that they come up with in this paper are clever. Some of them were already existed. Like in my first bullet point here, we have gpipe, which is an old program that did effectively the same thing, just on hyperclusters. So the basic idea of gpipe that Varuna borrowed was, let's data parallelize. Let's not use the same data for each batch. Let's have different batches within a huge batch, a macro batch, and let's divide that up into smaller chunks that we can push through these models, save each time, that's checkpoint, save our progress and push more. And at the end, we synchronously bring these model weights together to create a full picture of what the model looks like at that point in time. So that was borrowed from gpipe. Varuna, one of the main contributions that they made in this paper is they optimize over the batch size for the network bandwidth. So they ran into the problem of, we can't send this huge batch of data, even if it's a micro batch, over the network all in one go, without first thinking about how we lay out these machines in order to get the most out of the network and the most out of the machines. So, and we'll talk about the optimization problem that they solve in a little bit. And of course, if machines go down, you have to somehow reconfigure the job to run on the new machine that takes its place. So that is the semantics preserving part, right? That's the reconfiguration of the training job so that nothing gets lost, or as little progress gets lost as possible, so that the efficiency of the whole entire pipeline is not affected, or is affected as little as possible from one machine or some number of machines going down. And of course, Varuna obfuscates the GPU configuration, and that's done with job morphing for the individual GPUs. So before the code is compiled, it's pushed to the GPUs and then they compile it there, instead of the user having to do that. So one very important part of this paper that is a little bit machine learning-y is the way that the paper decides to parallelize the model. So of course, this model of 175 billion parameters, each parameter takes about a byte of data, maybe 2 bytes of data. I'm sure that I'm no mathematician, but that's a lot of data that this model here, represented by this huge blue box, is taking up. So of course, we can't store that in one machine. So you have to devise these cut points. That's what they call them, these partitions. And the way that you do that is, it matters a lot. So Varuna takes a lot of time to go over how to be efficient with data, the data parallel training, and how to be efficient with how you store your models and where you store your model partitions. So they spend a good amount of time talking about the interlayer partitioning, which is the form of partitioning that they use, and the one that's going to be most important to us talking about this paper. That's going to be splitting the model into different layers, so keeping the layers intact, so that this becomes a pipeline state, or this becomes a machine that's running here, and this becomes a machine that's running here, and this becomes a machine that's running here. Please note that it doesn't necessarily, just because the picture shows it like that, doesn't necessarily mean that there's exactly one layer per GPU. This could be any number of layers that happen to fit on that GPU to fully utilize the memory that lives on that GPU. And intralayer partitioning is the one that Varuna talks down to a lot. This is splitting the model across its connections. So that would mean that, hey, if you're training, the reason that they don't like it is that, hey, if you're training this layer, you have to wait for the input activations of all of these different machines, GPU1, GPU, and so on. So that's the reason that they talk down to this when scaling via more machines, throwing more machines at the problem. And the reason that interlayer partitioning is good is that, hey, if you throw more machines at the problem, you can split up these models better. and you can afford to have even grander models than 175 billion parameters. You can have just throw more machines, bigger models, no problem. And you don't pay for it in the pipeline efficiency cost that the intra-layer partitioning you pay for. So here we're going to talk a little bit about the data optimization and the optimization problem that they solve in order to get these replicas and these VMs working most efficiently. So the basic idea here is that we already know how the model is partitioned across these different VMs. So this is one type of VM. GPU1 would be here, GPU2, and so on, that store some number of layers. But each of these VM clusters, these subclusters, mini clusters, have some number D of data parallel replicas. And basically, And basically what that means is that this number D of data parallel replicas, they use different data, they push through the pipeline, different data, so that they can be as efficient with the data and training as possible. And then at the end, they combine their model weights to reach some sort of consensus between, hey, I learned this, hey, you learned that. And they do that for those D replicas in each GPU configuration. So please note that these are different VMs that I'm talking about here, but I just say GPU1 here to keep with the language of what's actually going on, that this is the same configuration, same model parameters as this GP1 here. And it goes on, so on down the line. So this is that optimization problem that I referred to earlier, and this is how they make it as efficient as they see fit. So a little bit about the schedule, which they also improved upon to get these models training as fast as possible, is if you look here at the GPipe schedule, you can see this large bubble, this large bubble where the pipeline isn't doing much. And so they try to minimize these bubble sizes, mainly due to the way that they configure the jobs to run on the machines and due to the way that they schedule. So here, if we look at Varuna, we see that, first let me tell you about what the F, B, and R mean. So F stands for the forward pass. The forward pass is when the data is fed through the layers and the activations are computed. So this forward pass is computed for this partition here, S1, and each of these S's stand for a partition of the model. And then this activation gets fed into S2. That's why S2 is waiting here. It's waiting to receive F1, the computations from F1, and then likewise S3 is waiting, and likewise S4 is waiting. So these machines, they compute all of their forward passes, and then eventually they receive the backward pass from the last model. It is absolutely necessary that these models wait for the backward pass to be applied, be calculated at the last machine, and then applied backwards. So as listed here, you feed into the K+1 layer, that's this part. You wait for the sync gradient that comes from this B, which is a backward propagation pass. That's what the B stands for. Then you have an R, which stands for recompute the forward pass. And we're going to talk about why we do that in a second. And then you apply the gradient weights to your layer, that's the B. And then after that, you do that for as many backward passes as you have, and you do that until it cascades. And then after this whole batch is done, this is an example of a data batch. So these machines were given the data across the replicas. So in fact, you would be correct to say that S1 is actually a collection of machines. That's correct. S1 is a collection of machines as described here. They have D number of data parallel replicas. So after all of these backward propagations have been applied, then there is a checkpoint. So that is the checkpoint after the mini batch of data. And that is more efficient than, you will notice that GPipe also recomputes instead of caching the results. So R4 here refers to the results of F4. You'd be correct to say that, well, F4 and R4 compute the same activations. And yes, you'd be absolutely correct. Backpropagation 5, it only applied to F5, the activations of F5, and then you do F4. But the main idea here is the reason that we recompute is that if we were to store those activations from the forward pass, you're talking about much more data than would originally be thought. So in this program, we mainly care about the scaling with respect to the model parameters. So we want it to be such that if I give you a much larger model, let's say I give you a model with a trillion parameters, 10 times as much as you've previously seen with the 175, I would like it to be such that we throw more machines at the problem and we get it to scale. Well, if you cache, you make an assumption of how much memory you're going to need to cache. So currently with 175 billion parameter model, you have approximately 3.5 megabytes of data per layer. So we can't necessarily assume the number of layers that live per VM configuration. Could be 10 layers, could be 100 layers, could be who knows how many. And for scalability in the future, you absolutely can't assume the number of layers. So you would need to recompute. And that's just the way it is. You may think it reduces efficiency. However, GPUs, their main job is matrix multiplication, or I'm sorry, matrix operations. So this is relatively quick, very snappy on a GPU. So the forward pass is not actually what takes the most time. I would argue what takes the most time is reapplying the gradients, waiting for the gradients, and transmitting the data over the network, of course. So a little bit of discussion of this magical Varuna manager that manages this entire fiasco that we have explained above, all of these machines. So this manager keeps a heartbeat with each of these machines, and it schedules them tasks that it has in its backlog that need to be completed. So upon startup, all of these partitions are predetermined from that optimization problem that we talked about. There are P number, or the pipeline length number of partitions that cut up the model. And then the manager, it optimizes all of these different configurations. Like for example, partition 48 might have a different GPU than partition number 25. So the manager needs to be aware of this fact, and it needs to notify or send the correct model size to each machine. So that's what the manager tries to do. It tries to square the circle in this respect. The manager also detects the slow and dead VMs, and it tries to replace them by job morphing them as well. So it brings up a new VM with the Scalable Cloud API, where you can bring up as many VMs as you'd like, and it tries to get it back up to speed with a checkpoint, and it to the best of its ability without restarting the entire checkpoint. And this is by reconfiguring the cloud deployment via those APIs that I just mentioned. So here we'll see some very interesting things when we're looking at this picture. So we see the red corresponds to the forward pass, and then you'll see that these machines end up waiting. And the reason that they wait is because they need to know what 48 thinks about the backward propagation, right? So then they cascade back down. So you have this pattern of relatively bubble-free. I would say that this is a significant bubble. So if you can reduce that weighting, of course, that would be better. That is for a lack of data, of course, because in the real world, you never have as much. Of course, these machines, you would prefer them to be chugging away data as much as they can. However, the lack of data, you can't always do that. So after that, you see an interspersing of these recompute forward passes and then the backward pass. Once they all agree, then they have an all reduce. So this is just a snapshot this is just a point in time of one pipeline, one data parallel pipeline pass. So after this all reduced, they would checkpoint, give me a new batch of data, and continue if you haven't. So let's talk a little bit about the results that Varuna was able to achieve. And this first slide here is a very kind of technical slide where they try and explain why they decided to use synchronous gradient applications. So you might say that, hey, we shouldn't be doing this. We shouldn't wait for this machine for the backward pass. Let's asynchronously do it and apply it as we go. And that's in fact exactly what Partitioning does, right? It does it asynchronously. Yes, asynchronously. And this one, it depends on the model, and it depends on a lot of different, and if you, I'm sure that depending on how you run this and how the race conditions happen, that this may actually converge just as the right picture. But what happens is that without the synchronous gradient descent, this model fails to converge the optimal parameters. Even though they're given a similar number of time steps. So at the similar number of time steps, they both fail to converge. Oh, or I mean, I'm sorry. At a similar number of time steps, Partitioning fails to converge, and Varuna does converge. And this is with the same 2.5 billion GPT-2 model. This slide here, we're going to be discussing another result of this Varuna program. So Megatron was another state-of-the-art deep learning training program, and we're training on an 8.3 billion model in this one, in this left picture, and a 2.5 billion model in this right picture, just to see how the scale of the model affects the efficiency of each. So starting with this 8.3 billion model, we can see that when you run Varuna on a hypercluster along with Megatron, this tight hatch pattern shown here. So it still does much better than Megatron, just due to the pipeline changes that they were able to achieve. So this experiment right here, these two grouped together, this is the same number of machines in the hypercluster, same hypercluster. So this is apples to apples, same model comparison between Varuna and Megatron. And then, of course, when we take them off the hypercluster and onto these low cost, low priority VMs, Varuna, which is designed for that, to be fair, does much better than Megatron even did on the hypercluster case. So, and Megatron, you can see in the plain white here, is not doing too well in terms of efficiency. And here, if we look, we have a 2.5 billion model, which is a smaller model, so we would expect better performance because of the efficiency that comes with smaller models and how you can pack them. And here, of course, we see the same type of story. We see that Varuna, when run on a hypercluster, does much better than Megatron did. And then when you put them on low cost, low priority VMs, it's the same deal as over here. Varuna was made for that. So talking about the major outcomes of this paper, the training throughput of Varuna is up to 17 times faster than the previous cutting edge deep neural net training software. It also cuts costs by 4 to 5 times when compared to the hyperclusters that they were originally meant to run on, or originally used to run them. Varuna can be used with existing models. So no matter how or what model you give it, you don't have to make any assumptions of the GPUs. You don't have to program or define models in a way that it favors one GPU over the other. Varuna does its best to morph your job, and it's user-friendly and scalable for that reason. You can just plug and play. One thing that I would like to say here is that these tests were run on Azure, and the exact configurations of these models I do not know at the current time, but if anybody is curious, I can link to the page in the paper where I know that it exists. But other than that, here is the open source link for where you can find the source code. And thank you for listening to my presentation.